Thanks, Ali. So Eric Topol talked about deep medicine, which is good, but how about with some even deeper medicine? Might be even better. Let's see. Probably not. No, that's okay. I have no medical background, or at least before I saw this chart, I had no medical background. This is 2014. I was an entrepreneur and a data scientist. I had sold a couple of companies, and my third one was doing well, and I thought maybe it's about time I tried to do something good in the world. And I was at a World Economic Forum event, and I saw this chart which says that in the developing world, this particular case is Nigeria, but every developing country looks about the same, there's about a 10x to 20x shortage of doctors. And the World Economic Forum analysis guessed it's going to take about 300 years to fix this problem. That seems too long to me. I didn't know anything about medicine, but I do know something about being a patient, and I know that when you go to a doctor, they look at all kinds of data, and some of the data they looked at was images. And as a data scientist, at that time I was at a company called Kaggle. We saw a lot of leading edge research, and I saw again and again at this time that image analysis was smashing state-of-the-art and human performance for analyzing images. For example, this 2014-2015 study at Kaggle was showing dramatic improvements in diabetic retinopathy performance by using deep learning. Now, this one particular algorithm or classes of algorithms, deep learning, was again and again, back in those days in my field, beating all the records. And I thought, oh, what if computers could help with medical imaging? So I started a company to test this out. And before I did some research. I thought, oh, let's go to MICI, the premier academic conference for medical imaging, to see how deep learning is being used in medicine today. And the answer was, it's not. I found a single example of a single paper presented at the conference, which was actually in histopathology. And in this workshop for machine learning and medical imaging, basically no one was talking about deep learning. I went to RSNA, the main conference for radiology. I talked to everybody. Nobody had heard of deep learning. Nobody was interested in deep learning. I thought, okay, well, let's try it anyway and see what happens. I tried it. I put together a team of 4 people. And within 2 months, none of us had any background in medicine. We had something that, compared to a panel of 4 human radiologists, had a much better false negative rate and false positive rate for finding malignant lesions in lung CT scans. So that started getting some people interested in what we were doing. This was a really important problem to solve because currently the vast majority of diagnosis of lesions is at this stage where the chance of survival is 10x worse than if you get it at this stage. This stage was the point at which our algorithm was able to reliably detect them. So I thought, wow, this is exciting. This is something which, if put in the clinic, could have a 10x impact on survivability just by earlier detection. So we launched this company. There was a lot of excitement in the kind of the tech press and the venture press. This is back in 2014, 2015. The reaction in the radiology forums was quite certain that this was the next Theranos, that I would be up here in a black turtleneck sweater. The reaction from the radiology trade press was, oh my God, they're coming for our jobs. So, you know, never think too much about the early reactions to any new technology. Later on, within 2 years, everybody was pretty much on board. At RSNA, there were queues out the door. RSNA was launching AI councils. With, you know, a month ago, journals were saying at Stanford, don't even submit stuff to us anymore showing superhuman performance at recognizing images, because we already know that's done. So things have moved fast. And as Eric Topol mentioned, we're now at the point where that thing I showed you, the Kaggle project, is actually now in the clinic and is making great results. And by the way, remember, it's 4 to 5 years from the point at which researchers like me know that something works to the point at which the New York Times tells you that it's actually been tried in the clinic and found it works, right? So it takes a long time. So then I started hearing all the other complaints in radiology. Oh, this is a waste of time because computers aren't better at radiologists. Radiologists do all these other things, which completely ignores the point that no one's trying to build things to replace doctors or replace radiologists. The kind of things we're building are things that fit into a medical system to try and make, in this example, radiologists dramatically more productive and make less errors, right? So the things that we really want to be caring about is what's the impact of deep learning when combined with human experts? For me, the thing I care about is can we get over this 10x shortage of doctors, which is going to take 300 years to fix? And based on the kind of research we were doing in our startup, we thought the answer is yes, we can see 10x improvements in productivity. So I think this can solve this huge problem which impacts most of the world. And remember, developing countries are not poor countries, they're developing countries. In fact, most IT spend in medicine today is in developing countries, right? They have cool equipment. They just don't have the people to interpret it. Then I started hearing the complaints, we can't start automating anything because if we automate things, it'll make the radiologists sloppy and they'll start missing stuff. Honestly, this is the complaint we hear in every single area where people start adding automation. And it's always true that you do have some problems, like the recent 737 GO accidents caused by over-automation. But overall, in every case, we see safety improves when humans are able to remove some of their cognitive burden from data ingestion to focus on data interpretation. It also means, most importantly to me, one of the things Eric Topol mentioned, more time for spending time with the patient, more time on empathy, less time on humans doing data analysis, because humans aren't good at data analysis. I also hear the complaint that this is just another fad. Let me just point this out. This is a fad which has been 60 or 70 years in the making. This was the first neural network in hardware. Right? It's a fad that people have been working a long time to get to the point where it's finally started working. Right? So if you think that we've got to the point over the last 60 years where suddenly it's now a fad, I can promise you it's going to keep going at this rate over the next few years. I also hear that deep learning is just another tool, don't take it too seriously, it's just hype, it's just another machine learning thing. It's not just another machine learning thing. It is indeed a machine learning algorithm, but it's one that's based on a mathematically provably infinitely flexible function. It's one that we have an algorithm that can do all-purpose parameter fitting, and as you just heard, the GPUs that it runs on are so fast and scalable that for things like genomic analysis, it's dramatically faster than our previous approaches, right? And so if you really believe this is just another algorithm of no particular interest, let me ask you, can your random forest and support vector machines understand human speech better than humans can? Because deep learning does, right? It is a very genuinely exciting algorithmic development that within lots and lots of areas we're seeing breaking all kinds of records and doing things computers couldn't do before. But it's not just for images. And it's not just for radiologists and pathologists and people doing diabetic retinopathy. I started this self-funded research lab called fast.ai. The reason it's self-funded is because I decided to focus on things that were practical rather than things that were grant-worthy or publishable. So I focus on things that are entirely not grant-worthy and not publishable. But one of the things we did was we built an algorithm for understanding text. It dramatically broke the state of the art again in text classification. And since then it's been built on by OpenAI and Allen Institute and Google and others. And OpenAI just recently announced that they took it to a whole nother level. Just to give you a sense of how this works, for those of you that have done some philosophy, you might be familiar with the famous John Searle Chinese room experiment, which is basically this idea, the way our algorithm works, and it has a long academic history before us, is our neural networks try to predict the next word of a sentence, basically, right? And we then use massive corpuses of documents, and so all it knows is language. And so this famous John Searle thought experiment was, can something that's only ever seen language, only ever seen syntax, learn any kind of understanding? And it's rare that you get an answer to a philosophical question from a computer science experiment, but OpenAI tried this experiment at a massive scale. They created a language model that read a huge amount of the World Wide Web. And then they took that language model and they said, here's a sentence that we will write. So a human said to this language model, in a shopping finding, scientists discovered a herd of unicorns living in remote Andes mountains. The researchers were surprised that the unicorn spoke perfect English. And then they said to the computer, finish this story for me. And remember, this computer algorithm's done nothing but learn to predict the next word of a sentence. The computer said, Dr. Jorge Perez, a biologist from the University of La Paz, which is near the Andes, were exploring the Andes. They found a small valley, blah, blah, blah. They ventured further in. By the time we reached the top of one pig, the water looked blue with some crystals on top, said Perez. So it's actually using the same person's name. They're astonished to find a unicorn herd. They could be seen from the air. They were so close they could touch their horns. And then these bizarre creatures, they discovered the creatures also spoke some fairly regular English. We can see, for example, they have a common language, something like a dialect or a dialectic. So this whole story was written by a computer that had never been programmed with any rules, any knowledge about language, any knowledge about unicorns, just a deep neural network which just read the internet. So, it's extraordinary, what these things can do. And so when you think like, what can we do in medicine with deep learning, this is where you need to be thinking, right? So when you look at a company like Google, which was kind of the first company to really invest in deep learning, so they, in 2012, hired Alex Krzyzewski and Jeffrey Hinton, who were the people who kicked off the modern deep learning revolution when they showed a kind of world record performance on an important data set called ImageNet. And what they did was they created this group called Google Brain. And Google Brain was a small group in Google that went round from department to department telling the people in that department of Google, there's this thing called deep learning, and here's what it can do, right? And then over the years, this cuts off at 2016, so I don't have more recent data, they continually at Google exponentially increased the number of projects at Google that used deep learning. So today at that company, basically everything uses deep learning. The way the human resources looks at resumes helped by deep learning. The way their cooling systems are run is helped by deep learning. They got a 40% improvement in cost as a result, saving them billions of dollars a year. You might have seen in the last 2 days, they've made it so that now your mobile phone, if you have a Pixel phone, actually has a deep learning neural network running on the phone, which does real-time voice transcription without even going to the server. So this gives you a sense that this algorithm is so incredibly flexible that a company that's really invested in it, it's kind of taken over everything they do, and they're making a whole lot of money as a result. But it's not true that you have to be Google to do this. It really is not true. In fact, at fast.ai, most of our projects and our students' projects use a single GPU. In fact, most of them use rented GPUs. So at Cressel, for example, you can rent a GPU for 30 cents an hour. This is the norm, right? This is what most practically impactful projects in the real world I've seen use a single GPU. You can buy one of, well, not this particular one, but you can buy a good quality GPU for about $500, and often they'll come with 3 free computer games as well. So it's a real bonus. So for example, we wanted to show what's possible for normal people. So we took that ImageNet data set I told you about earlier, and we actually set a world record for how quickly you could train it. Previously, people generally took multiple days to train a model for the ImageNet data set. We showed that we could train it in 18 minutes for $40, right? So this kind of cutting edge level performance in deep learning is now really accessible to normal people in normal departments. And I say normal people because I keep hearing we don't have deep learning people. Well, do you know where deep learning people came from? They learned about deep learning from courses, right? So what we did was we created a course, and because we're self-funded, that means we can do it, we can provide it totally for free with no advertisements, where anybody can learn to do this. And they have, right? There are now hundreds of thousands of people that have done this course. And what we do is we say, hey, here's a place on this community forum we've created where anybody can share their work and tell us what they've done. And there's now thousands of examples of people who have said, okay, after the first lesson of 2 hours, here's what I've done. People who have graduated from this course have gone on to all kinds of cool stuff. For example, Alex is a radiology resident from Canada who won, so he's the best in the world at pneumonia detection. So he's a radiologist who's now one of the world's best deep learning practitioners, right? And he's also writing academic articles. Melissa Fabros, another one of our students, won a huge prize for her work with helping to identify people of color in images, which is something that traditionally these algorithms have been bad at. One of our students, Melissa, by the way, was previously an English literature PhD. Hamal Hussain at GitHub was previously a lawyer. He's now building their most powerful natural language recognition systems at GitHub. Christine Payne at the famous OpenAI Institute is building algorithms that actually write music. She used to create music herself on an actual piano. She was a musician. So there's lots of examples of people who are like learning deep learning and doing super cool stuff. And these people and you do not require Google-level amounts of data. Here's one of our students, and this is the norm. Students keep on showing us. I just grabbed 30 images, and I built a 100% accurate on a holdout validation set thing that can recognize cricket versus baseball pictures. Like, for the vast majority of problems you have to solve, including my experience problems in, with medical imaging, you don't need much data. And the trick is to do something which you heard about earlier, which is transfer learning. You start with a model that's been pre-trained on something else, and you fine-tune it for your particular problem. So for example, in this case, you started with an ImageNet model, which had never seen cricket and baseball before, but knew how to tell dog breeds apart, and 30 images was enough for it to learn about cricket versus baseball. So what does this mean? Well, with transfer learning, people have shown in recent academic research examples of how a single model can be transfer learned to do many different kinds of tasks. It's been shown that a single transfer model can get state-of-the-art performance on many different data sets. It's also been shown something very similar for text, not just images. With transfer learning, you can do a small amount of data, a small amount of compute to get state-of-the-art results. Google do something similar, in fact, for the machine translation. They can actually translate between language pairs for which they've never actually seen two documents in those two different languages. Because through transfer learning, their system is actually able to translate between arbitrary language pairs. So the cool thing is, for transfer learning, you can download from various model zoos on the internet a pre-trained model to do something vaguely similar to what you want. And so this is a very big website. We can start here. We can zoom out a bit further, zoom out a bit further. There are lots and lots of pre-trained models. So you could jump on here and search for medicine to get back a medical pre-trained model, and oh, it's empty. Why are there no medical pre-trained models? I don't know. Like, people are doing all this research, but they're not releasing the actual thing that would make the biggest difference to the world, which is, here are the weights we created. Right, so here's a huge gap, literally. That white thing should be full of, you know, brain CT, brain MRI, radiology report, NLP, 12-lead ECG. They should all be here, right? Currently, they don't exist. But here's the really cool thing, is we can then take models of lots of different types of data and combine them all together into one big model that combines all this stuff together. Again, this is not technically out there. This is stuff that's totally standard day-to-day stuff at companies like Google. We do it all the time. Hasn't happened in medicine yet, right? But it totally could happen. And if that did happen, with a data set like that, we could have something that doesn't just say, here's your diagnosis, but here's the exact probability of success of each of these possible medical plans working for you. Like, truly precision medicine, right? And the interpretability would be like, here are 5 people all around the world that looked exactly like your patient. Here's exactly what happened to them when we gave them exactly these things. So then the doctor can really use their domain expertise, because we're not giving them data, we're giving them examples, right? We're giving them something that doctors really understand. One of the problems here, of course, is getting the data together from all of these different areas. So doc.ai, which I'm involved with, has a really cool approach to this, which is they say, hey, you know what? Patients own their data. Let's give them an app they can download and grab all of their different data from different places, ask them to opt in to then sharing that so that that consolidated data could be used by lots of different data science projects. So there's one way to solve this problem and get this kind of even deeper medicine. The second way, which is also something that doc.ai is involved in, as are lots of other people, is you don't actually even need to share the medical data. There's a thing called federated learning, which is basically Harvard could train a model, and then they could send some weight updates to Stanford to say, as we train model on our data, this is how our model changed. Stanford then can share their model updates, and they can share their model updates with Shanghai Jiaotong, and they can share their model updates with Apollo, and it comes back to Harvard. And kind of a cooperative group of hospitals like this, the research shows that just sharing model weight updates and not even sharing data at all gives you the same performance as actually sharing the data. Right? So we don't even have to deal with this problem of de-siloing the medical data to get the same benefits. So to try and help people get started with this, I recently helped launch a new center at the University of San Francisco called WAMRI, thanks to the generosity of Wicklow. The way we're doing this is you can literally send us, if you're a doctor or a researcher, you can send us your data. We will analyze it for you. We will co-publish an open academic journal. So if you know your medical problem, right, and we know how to do the deep learning, then we can work with you to actually co-publish a paper in which we bring these two pieces together. And at the same time, we will try to help you, teach you to become effective deep learning practitioners yourself. So if that sounds interesting, please contact at wamri.ai, because we would love to work with you, particularly if you're interested in either pre-training a model that you could share with the rest of the world, or helping to integrate multiple data sources to get to this true, even deeper learning approach. Thank you.